So next, I want to mention some previous results that can be viewed as results addressing question 1. Notice that I'm putting quotes around the words GL analogs because the analogy with minimal submanifolds may very well not have been the original motivation for these authors. For example, the study of stable solutions to elliptic semilinear equations is a very old subject, perhaps as old as the Lawson-Simons result. So this is really a way for me just to put things into perspective. The first result I want to mention is from the mid-90s. It's due to Jimbo and Morita. And they proved that on a convex domain in Rn, if you have a stable solution to the Ginzburg-Landau equation, no restriction on epsilon, satisfying the homogeneous Neumann boundary condition, then U is constant. Okay. In the same paper, they suspected that this is true with convex replaced by non-simply connected. And in that paper and subsequent work, they produced non-constant stable solutions on some non-simply connected subsets. Okay, and they asked the question whether their theorem is true for with convex replaced by simply connected. In 2005, Silvia Serfati addressed that question when n is 2. So she proved that if you have a simply connected subset in R2, assuming that epsilon is small, then stable solutions to the Ginzburg-Landau equation with homogeneous Neumann boundary conditions are constant. Notice this extra smallness condition that wasn't there for the Jimbo-Morita result. That's due to the difference in the method of proof. So for Jimbo and Morita, they made a clever choice of test functions in the second variation, much like how Lawson-Simons proved their results. And for Serfati, she related the second variation of the Ginzburg-Landau functional to the second variation of a limiting functional. Showed that stability passes to the limit, and that the limiting functional does not admit non-trivial stable critical points. And so her method therefore puts a smallness requirement on the parameter epsilon. Now, interestingly, in higher dimensions, for example, in dimension 3, so Montero, Sternberg, and Zimmer constructed simply connected subsets of R3 that admit non-constant stable solutions. So some simply connected sets in R3 admit non-constant stable solutions. Okay. So a couple of years later, Serfati's method was generalized to Riemannian manifolds by Rong Cheng. So Chen proved, among other things, that on a Riemannian two-sphere, with positive Gauss curvature, there are no non-constant stable solutions if epsilon is small. So epsilon is small implies that stable solutions to GL epsilon are constant. Okay, so these are all stability implies some triviality type results. And you can see them as analogs of the result of Simon's, which says that there are no stable minimal submanifolds in the sphere. Now, recently I obtained some results along these lines. So I'll state my result in two parts. First, if you look at solutions to the Ginzburg-Landau equation on Sn or Cpn with their standard metrics, then they have to be constant. Cpn are constant. Okay. The second part, so part one is true with no restriction on epsilon. Part two requires a smallness assumption, like in Serfati and in Chen's result. So I'll state it in the following way. For all C positive, there exists a threshold epsilon naught such that if you have a stable solution to the Ginzburg-Landau equation on Sn with parameter less than epsilon naught, then it, okay, so if U solves dl epsilon on Sn with epsilon less than epsilon 0 and satisfying these upper and lower energy bounds. Okay, then the Morse index of U as a critical point of E epsilon is at least 2. So this result is an analog of Simon's index lower bound for minimal submanifolds in the sphere. Right, and it says that under these conditions, critical points of the Ginzburg-Landau functional satisfies the same index lower bound as codimension 2 minimal submanifolds in the sphere. Okay. So now let me make a couple of remarks about the theorem. So first of all, I'm currently still trying to figure out whether this lower bound in part 2 is optimal. And if it is, what do the solutions attaining this bound have some symmetries, as in Simon's case? Okay. And secondly, part 1 on CPN can be viewed as an analog for Lawson-Simons. Now, you are asking where are the complex submanifolds? My argument is that we are in the homologically trivial case, and there are no homologically trivial complex submanifolds because they are homology volume minimizers. Okay, so why are we in the homologically trivial case? Because if you take a solution to the Ginzburg-Landau equation on your closed manifold, by the maximum principle, you just hit norms U squared with the Laplace operator. By the maximum principle, you see that solutions to the Ginzburg-Landau equation takes values in the unit disk. Which I've drawn on the left. And so let me just say the conclusion and then explain using that picture. Heuristically, level sets of U are homologically trivial. So if you take a value z inside of the unit disk, and you take another value outside of it, you draw a line between them. Now, the preimage of L under U would be, roughly speaking, a codimension 1 object connecting the level set of Z and the level set at W. But if U maps into the unit disk, and then the level set of U at this value would be empty. And so the conclusion is that the level set of U at Z bounds this codimension 1 thing, which is the level set of L, the preimage of L under U. And so that's why I'm saying that the level sets are homologically trivial. So we're sort of in the homologically trivial case here. And if your homology class is trivial, then there are no non-trivial complex submanifolds in it. Okay, and you ask, then how do we capture the homologically non-trivial case? Well, the answer may lie in the U1 Higgs approach. So the U1 Higgs approach provides actually a very natural analog for complex submanifolds. It might be the right setting to ask this question, to look for a complete analog for the Lawson-Simons result. And I'll explain the framework in the case of Riemann surfaces, even though we really care about the higher dimensional case. So it's an observation due to Bogomolny from the mid-70s that in the notation from the end of part 1, the U1 Yang-Mills-Higgs functional can be rewritten in the following way. Sigma is our Riemann surface, or let me still call it M. Here I'm just recalling the definition of the functional. The thing is this, so it's 1/2. The precise expressions are not that important, but I'm going to write them down. And I'll tell you which aspects you should focus on, but it's not the precise formula. Now, let me remark that this is the degree of the line bundle up to a factor. So it's a topological constant, and it does not depend on your configuration, on your choice of U and nabla. Now, you should focus on 3 things about this formula. First of all, these 2 terms are non-negative. Secondly, their vanishing is equivalent to a system of first-order equations on U and nabla. Number 3, this number here is topological, does not depend on U and nabla. If you take those 3 things together, you draw the following conclusion. G epsilon is always bounded below by 2 pi times degree of L, and equality holds if and only if the following first-order system is verified. And number 3, solutions verifying this first-order system give you minimizers for the G epsilon functional. Okay, so this is called the vortex equation, and I'll denote that by VE sub epsilon. Okay, so what have we got here? We have a first order system of equations providing critical points for the relevant functional, verifying a topological lower bound. This is completely analogous to what complex submanifolds are for the volume functional. Okay, and solutions to the vortex equations are critical points because they are minimizers. So they're not only critical points, right? They're stable critical points. So this is just repeating what I said up there. You have a first order system of equations providing critical points for G epsilon attaining a topological lower bound. And that's completely parallel to the role played by complex submanifolds for the volume functional. And furthermore, that derivation I just did on the previous page is generalizable to Kähler manifolds, and that's the work by Stephen Bradlow and Oscar Garcia Prada. And now the question is, since you have these objects that seem to play the same role as complex submanifolds, you could ask whether the Lawson-Simon theorem is true. So whether stable critical points of G epsilon have to be solutions to the vortex equation. Stable critical points. G epsilon. Let's assume again, degree non-negative. This is a question mark. Must they be solutions to the vortex equation? Okay. So I obtained sort of a partial answer very recently. This is true on S2, so CP1. Provided either you assume that the section part is not identically zero, or epsilon is below a certain optimal threshold. Optimal threshold. Okay, so given a stable solution, a stable critical point to G epsilon on S2, and assuming either of these conditions, then you get that they satisfy the vortex equation. Okay, and current work in progress is to generalize this to CPN for n bigger than 1. Oh, I should say here that this is on CPN. Okay, so and that's pretty much all I want to say in this part 2 of my talks. So in part 3, we'll return to the Ginzburg-Landau functional, and I'll explain how to prove one of my results stated above. Okay, so thank you again for staying until the end. Thanks for your attention, and I'll see you in part 3.